Hey guys, alright, let us get started on talking about covalent molecules. We'll be diving a little bit more deeply into these guys because they are where things get confusing and difficult. Ionic compounds are fairly straightforward, and we're not actually going to talk much about metals, which gives me a sad because they're kind of awesome. Alloys, ceramics, things like that. But let's go into molecules. As you can see, there won't be much in the way of math in this particular section. So let's once again cover the fact that you need the stable octet. Okay? So when you're building a covalent compound, you need each atom to have a stable octet. And when you make a bond, the pair of electrons inside that bond counts toward each atom. Okay, so let's go through a few examples here. Okay, so the halogens are all like this. Okay, X standing for halogen, and they have 7 valence electrons. Okay, so this could be chlorine, fluorine, iodine, bromine, doesn't matter. And here's the other of that same one, which also has 7 electrons. Okay. Now, each atom donates its unpaired valence electron to form a bond. Okay. So, when you look at, let's move it a little further down, when you look at each atom, what does each atom see? Well, this atom sees 2, 4, 6, 8 electrons. Because it looks at that bond and sees 2 electrons, it's happy. Okay? And similarly, this one sees 2, 4, 6, 8 electrons, so it's happy. So each atom sees a total of 8 electrons, even though there's not a total of 16, there's only 14 electrons. Okay? So that is how covalent bonds work. That's why they make things happy. Let's move a step to the left and look at oxygen. So every oxygen atom has 1, 2, 3, 4, 5, 6 valence electrons. Okay, so now each oxygen atom donates 1 pair of electrons, makes a bond, and it has to donate a second pair of electrons to make a second bond. That's another thing to note, that unpaired electrons are actually unhappy. That's another reason that they make bonds. So you're getting the stable octet and you're pairing unpaired electrons. So when you look at the bonded oxygen atom, this is what each atom sees. Okay? 2, 4, 6, 8. Happy. And 2, 4, 6, 8. Also happy. You can do something similar with hydrogen. Each hydrogen comes in with 1 valence electron. They donate them in, and they make a bond. Now remember that hydrogen only needs the 2 electrons, so this guy is quite happy right here. And let's finally look at nitrogen. Okay, so nitrogen comes in with 5 valence electrons, and it's going to have to donate 1, 1, 1, 1, 1, 1 to make 1, 2, 3 bonds to get all of its unpaired electrons paired and to fill out its stable octet. So this is a molecule of nitrogen. 2, 4, 6, 8. Okay. And now each nitrogen is happy. So that is the diatomic elements. So we're already seeing a couple of trends when it comes to covalent bonds. The halogens tend to only like to form a single bond. Likewise, hydrogen only needs to form a single bond, only can form a single bond. Oxygen likes to form 2 bonds, and nitrogen likes to form 3 bonds. And that's it. 3 is the max, the maximum number of bonds you can get between any 2 atoms. Any more than that, it would be way too crowded with electrons. It just doesn't work. It can't happen. All right. Another thing is that you'll see what are known as non-bonding pairs. Sometimes I abbreviate that as NBP. A non-bonding pair is any pair of electrons that is not taking part in a bond. Okay. So they play an important role later on, but they are not part of the bond itself. So those are known as non-bonding pairs. They just don't participate in the bond. All right, next, water. You'll recall I showed this to you back in the supplement that I made after covalent bonds. So here's hydrogen with its 1 valence, oxygen with its 6, and the other hydrogen with its 1 valence, donating electrons together to make a molecule of water. And water has 2 bonds and 2 non-bonding pairs. The next example I was going to show you was methane. Methane is CH4, as you'll recall. So here's carbon with its 4 valence electrons. Remember, when I first talked about Lewis symbols, I said we often draw them with the electrons unpaired. This is why, because it lets us put the bonds into place. Okay. So you get a bond here, a bond here, a bond here, and a bond here. And that's methane, a single carbon atom bound to 4 hydrogen atoms. And that is what carbon likes to do. Carbon loves having 4 bonds. It could be 4 single bonds, 2 double bonds, a single bond and a triple bond, a double bond and 2 single bonds. Doesn't really matter, so long as carbon has those 4 bonds. That's when carbon is at its most happy. And it can do that with other carbons. And what you get then is the structure of diamond. A networked structure that just keeps on linking carbon to carbon to carbon. Very, very strong stuff. Very, very happy carbon. All right, and then finally, pentane. Okay. Pentane, if you think back to our discussion of the alkanes, pentane has 5 carbons. So here's carbon, 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 and carbon. Dot, 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 dot. There's a reason we don't usually do this. Okay, so now we surround it with hydrogen. And here are our bonds. Each carbon gets 4 bonds. Each hydrogen gets 1 bond. And that is why carbon is really good for organic molecules, for making this stuff of life, because it can make these long chains just by bonding to carbon to carbon to carbon to carbon. Okay. Now recall, there are exceptions to the octets. Boron is one of those. It is happy just with 6 electrons or 3 bonds. Now nitrogen also makes 3 bonds, but nitrogen, you recall, ends up with lone pairs Okay, so here's ammonia, NH3, whereas boron trihydride would look like this. No lone pairs, just boron bound to 3 hydrogens, because it is happy with only 6 electrons. It doesn't need more, so it's happy with just 3 bonds. And recall that you can get expanded octets. So, for example, phosphorus pentafluoride. Okay. So the phosphorus, it looks around itself, it sees 10 electrons here, because it has the 3D subshell available. So that's where the extra bonding capacity comes from. And finally, you can have radicals. A radical is when you have any sort of unpaired electron. Unpaired electrons tend to be incredibly unhappy, so radicals are very, very reactive. If you ever listen to health food nuts or bad commercials and so on, they'll often talk about free radicals, and how they're bad. Generally speaking, they are. When fat goes rancid, that's because of free radicals forming inside the fats. And that causes just sort of a chain reaction of radicals spawning radicals, and it's a bad thing. Let's see, hydrogen peroxide, hydrogen bound to oxygen, bound to oxygen, bound to hydrogen. The reason that we use that to disinfect wounds or to clean rust off of iron is because it will spontaneously split into free radicals, 2 free radicals, looking like that, with an unpaired electron. Okay, and that is, of course, highly reactive. Another free radical, one that's actually fairly common in your biology, would be nitric oxide. You might recall I mentioned that as one of the common names out there. Nitric oxide is just a single nitrogen bound to a single oxygen, and it looks like this. Let's see. Okay. So this oxygen, see, has its full allotment of 8 electrons, but this nitrogen only has 7 electrons and a free radical. So the nitrogen isn't perfectly happy, not only because it doesn't have all the electrons at once, but also because it has that radical electron. Nitric oxide is actually used by your white blood cells to kill invading pathogens, because it's nice and reactive. It is also used to regulate blood pressure somehow. So one of the side effects of this was actually, I should say, it's not a side effect, it's actually intended in some blood pressure medications, was actually taking advantage of nitric oxide. And it dilated blood vessels, decreasing blood pressure. But it was sort of indiscriminate about how it did that, so it also caused terrible migraines. All right, so those are radicals, and those are things that show up not incredibly all the time common, but they do show up occasionally, and you need to know what they are and how they can participate in some forms of chemistry. So be able to recognize unpaired electrons and why those are unhappy. All right, so here is how we draw the Lewis structures that I've been putting out there. The Lewis structure is like when you take the Lewis symbols and you link them up using bonds. Okay? So what you're going to do is you're going to add up all of the valence electrons available, and you're going to surround the core atom, that's usually the one where there's only one of them, with satellites. That's what I call them. I don't know if anyone else calls them satellites, but those are the atoms that surround the central atom. And you draw one bond to each satellite. You're going to remove 2 electrons from the pool available. You remove 2 electrons for each bond. Then you're going to surround the satellites with non-bonding pairs. That's 15 minutes. I will go through one example, and then we'll come back in the next lecture. Let me turn off the timer really quick. All right. So you surround each satellite with non-bonding pairs, removing 2 electrons from the pool for each non-bonding pair. Obviously, the exception to this would be hydrogen. Hydrogen will never get non-bonding pairs. And next, if you have any electrons left over, you put them on the core atom as non-bonding pairs, and then you fill out the core atom's octet with double and triple bonds as necessary. Okay. So, just a quick example. Let's go with, let's just do water. Okay. So, hydrogen, oxygen, hydrogen. Okay. You need to add up the valence electrons. Okay. So hydrogen has 1 each, and oxygen has 6, giving us a total of 8 electrons. Okay. So now we draw 1 bond to each of the satellites. Each bond removes 2 electrons, so we subtract 4 from the available pool, leaving us with 4 electrons. We put non-bonding pairs in the satellites. Well, the satellites in this case are the hydrogens, okay? And hydrogens don't ever get non-bonding pairs. Okay? So the next step would be to put non-bonding pairs on the central atom, and that would be oxygen. So you remove those 4 electrons from the pool, leaving us with 0. And we're good to go. So in the next lecture, we'll do some more examples that will give us some expanded octets, some double and triple bonds, and so on.